Unit 2, Data Wrangling, Data Cleaning and Preparation, Part 1. In this unit, we focus on three important stages of data processing: data handling, data wrangling, and data cleaning. When dealing with large volumes of data, several challenges arise, such as memory limitations, slow processing speed, and difficulty in managing complex datasets. To address these issues, general techniques like data sampling, chunk processing, and efficient storage methods are used, along with programming practices such as optimizing code, using appropriate data structure, and leveraging libraries designed for large-scale data processing. Moving on to data wrangling, this method prepares raw data to a structured format which is suitable for analysis. Key operations include cleaning, transforming, merging, and reshaping data. For example, datasets can be combined using merging and concatenation, aligned using index-based merging, or reshaped through pivoting to organize the data more effectively. Finally, data cleaning and preparation ensures that the dataset is accurate and consistent. This includes handling missing values, applying transformations, manipulating string data, summarizing information, grouping data into bins or classes, standardizing values for uniformity, and identifying as well as removing outliers, noise, and anomalies. Together, these steps improve data quality and make it ready for meaningful analysis and decision making. Handling large-scale data presents several significant challenges that must be addressed for efficient processing. One major issue is the high volume of data, where datasets can range from gigabytes to terabytes or even petabytes, making it impossible to load them entirely into system memory. This necessitates the use of distributed storage systems such as Hadoop or cloud-based storage, along with techniques like processing data in small chunks. For example, a dataset with 100 million records cannot be accommodated in the RAM of a typical laptop. Another critical challenge is memory overload, as many traditional algorithms assume that the entire dataset can fit into memory. When this assumption fails, it may result in system crashes or degraded performance due to excessive swapping between memory and disk. To handle this, approaches like data streaming, generators, and tools such as Dash and PySpark are commonly used. Additionally, long execution time is a key concern, as processing large datasets can take a considerable amount of time, sometimes making the process impractical for real-time applications. For instance, training a machine learning model on a large dataset may take several hours or even days if not optimized efficiently. Another important challenge in handling large data is input-output bottleneck, where reading and writing large datasets become slow because of disk access speed is much lower than memory speed. Frequent disk operations can significantly delay processing, and the choice of file format also affects performance. To address this, efficient storage formats such as Parquet and HDF5 are preferred, and unnecessary disk reads must be minimized. Another issue is CPU starvation, which occurs when the processor is unable to handle the workload efficiently. This typically happens when too many processes compete for CPU resources or when inefficient code is executed, resulting in underutilization of system capabilities and increased processing time. Additionally, scalability becomes a major concern, as programs that work well for small datasets often fail or perform poorly with large data. This requires redesigning the system using approaches such as parallel processing and distributed computing, ensuring that the solution can handle increasing data sizes effectively without performance degradation. In large-scale data processing, there is often no one-to-one mapping between problems and solutions, meaning a single solution can address multiple challenges simultaneously. For instance, a technique designed to reduce memory usage may also improve computational performance, making it more efficient overall. A good example of this is data compression, which reduces the size of the data set and thereby minimizes memory requirements while also speeding up processing. By working with smaller data, systems require less storage space, reduce disk input-output operations, and enable faster data transfer. This leads to improved overall performance in both storage and computation. For example, using efficient file formats like Parquet instead of CSV significantly reduces file size and improves read-write speed. Similarly, compressing large data such as images or log files helps in saving storage space and enhances processing efficiently. General techniques for handling large volumes of data. Under this, we will discuss about problems, solutions, and general tips. Choosing the right solutions. Choosing the right solution is crucial when working with large-scale data, as inefficient algorithms can lead to very slow execution or may not even complete with a reasonable time. Big data processing requires scalable and optimized approaches that can handle large volumes efficiently. Another important technique is the use of online algorithms, which process data incrementally in a single pass without needing to store the entire dataset in memory. This is especially useful for streaming data scenarios, such as calculating a running average from live sensor inputs. Another effective method is block or chunk processing, where large data sets are divided into smaller manageable parts and each block is processed independently. For example, large CSV files can be read in chunks using functions like pandas read CSV with a specified chunk size, allowing efficient memory usage. Additionally, the MapReduce model provides a powerful framework for distributed data processing by dividing the task into three stages, splitting the data, processing it in parallel, and then combining the results. A common example is counting word frequencies in large text datasets where the map phase count words locally and the reduce phase aggregates the counts to produce the final results. Selecting appropriate data structure plays a critical role in efficiently handling large datasets, as the choice directly impacts memory usage, processing speed, and scalability of the system. Efficient data structures help in optimizing both storage and computation. For instance, arrays provided by libraries like NumPy are highly memory efficient and offer fast operations, making them ideal for numerical data processing. Similarly, data frames in Pandas are well suited for handling structured, tabular data and provide powerful functionalities for filtering, grouping, and analyzing data with ease. In addition, sparse data structures are particularly useful when dealing with datasets that contain a large number of zero values. Instead of storing all elements, they store only the non-zero values, thereby significantly reducing memory consumption. For example, in large matrices where most entries are zero, using a sparse representation can save a substantial amount of storage and improve computational efficiency. Data structures offer unique advantages depending on the type of data and the operation being performed. Arrays are highly efficient for numerical computations, providing fast processing due to their contiguous memory storage, making them ideal for mathematical operations. Data frames, on the other hand, are designed for structured and tabular data, allowing easy analysis through features like filtering, grouping, and aggregation. Sparse matrices are specifically useful when dealing with large datasets that contain many zero values, as they store only non-zero elements, thereby improving memory efficiently. Dictionaries are best suited for key value pair operations, offering very fast lookup times, which makes them ideal for tasks that require quick data retrieval. Choosing the appropriate data structure based on the use case ensures better performance, efficient memory usage, and improved scalability in data processing tasks. Using the right tools is essential for handling large-scale data efficiently, as traditional tools often fail when the data size increases beyond system limits. Big data requires specialized tools that are designed to handle high volume, velocity, and variety of data. For minimized size datasets, libraries like NumPy and pandas are highly effective, offering fast and efficient operations through vectorization. However, when the data grows larger and cannot fit into memory, tools like Dask become useful as they enable parallel computing while maintaining a similar interface to pandas. For even larger datasets at the petabyte or terabyte scale, Apache Spark provides a powerful distributed processing framework that can handle data across multiple machines efficiently. Additionally, Hadoop, which includes HDFS for distributed storage and MapReduce for processing, offers a fault-tolerant solution for managing and analyzing massive datasets. Choosing the appropriate tool based on data size and complexity ensures better performance, scalability, and reliability in data processing tasks. Choosing the right data structure. We will discuss about sparse matrix, tree data structure, and hash tables in the following slides. Sparse matrix. A sparse matrix refers to a data set in which most of the elements are zero or empty and only a small portion contains meaningful non-zero values. This type of data is very common in real-world scenarios, especially in large data sets where information is unevenly distributed, such as recommendation systems or text data representations. Storing all values, including the large number of zeros, leads to significant memory wastage. To overcome this, sparse matrices store only the non-zero elements along with their positions, which drastically reduces storage requirements. This approach not only saves memory but also improves computational performance. Since zero values are ignored, algorithms can focus only on the meaningful data, resulting in faster processing. For example, instead of storing an entire matrix filled with zeros, a sparse representation stores only the row index, column index, and the corresponding non-zero value, making it much more efficient for both storage and computation. Tree data structure. A tree data structure is a hierarchical model in which data is organized in the form of nodes, starting with the root node at the top and branching into child nodes across multiple levels, forming a tree-like structure. Each node can further have its own subtrees, making the structure highly scalable and suitable for large datasets. Trees are particularly useful for handling large data because they enable efficient searching compared to linear structures like trees where every element must be checked sequentially. In a tree, data is organized based on certain conditions, allowing a guided search process that follows a specific path to reach the desired element quickly, thereby reducing unnecessary comparisons. This structured approach significantly improves search efficiency typically achieving logarithmic time complexity, which is much faster than linear search. As a result, trees are widely used for sorted and structured data, providing better performance and scalability when dealing with large volumes of data. A hash table. A hash table is a data structure that stores information in the form of key value pairs, allowing efficient data retrieval. It works by using a hash function, which makes an input key and converts it into a specific index or location, often called a bucket, where the corresponding value is stored. Instead of searching through all elements one by one, the hash function directly maps the key to its storage location. This process involves taking the input key, applying the hash function to generate an index, and then storing or retrieving the value from that position. The major advantage of hash table is their speed, as they eliminate the need for sequential searching and enable nearly constant time access to data. This makes them extremely powerful and widely used in applications that require fast lookup, such as databases, caching systems, and dictionaries. Next is choosing right tool like num, explorer, bcalls, etc. We'll see them one by one now. Advanced tools are available to improve performance when working with large datasets in Python. Python enhances execution speed by converting Python code into C, making it particularly useful for computationally intensive tasks where pure Python may be slow. Num Explorer is designed to efficiently evaluate numerical expressions by utilizing multi-threading and optimized memory handling, which makes it highly suitable for performing fast operations on large NumPy arrays. Number, on the other hand, is a just-in-time compiler that accelerates Python functions during runtime, especially improving the performance of numerical computations and loops that typically run slowly in standard Python. Additionally, bcalls provides a powerful solution for handling large datasets by offering compressed columnar storage, which significantly reduces memory storage. It enables efficient storage and querying of data that may not fit entirely into memory, making it a valuable tool for big data applications. Blaze is a powerful tool that allows users to work with large datasets using an interface similar to NumPy and Pandas, making it easy to learn and use. It supports data from multiple sources such as CSV files, SQL databases, and large-scale data systems, providing flexibility in handling diverse data formats. Theano is a numerical computation library that focuses on efficient evaluation of mathematical expressions, and it has been widely used in deep learning for optimizing complex computations and improving performance. Dask is another important tool that extends the capabilities of NumPy and Pandas by enabling parallel and distributed computing. It allows users to process datasets that are larger than system memory and can scale computations from a single machine to a full cluster, making it highly suitable for big data processing tasks. General tips like don't reinvent the wheel, get the most out of your hardware, and reduce the computing needs. Databases play the major role in efficiently handling large datasets as they allow data to be stored, managed, and processed without loading everything into memory. By using databases, it is possible to create analytical base tables directly within the systems, which help reduce data transfer and improves overall performance. This approach is especially useful when feature engineering involves simple operations such as filtering, aggregation, and joins, as these can be efficiently executed within the database itself. For more complex computations and advanced techniques like user-defined functions and stored procedures can be implemented inside the database to perform customized processing. Instead of developing algorithms from scratch, it is advisable to use well-established and optimized libraries such as Mahout and Weka, which are designed for large-scale data processing. These libraries are thoroughly tested, follow best practices, and incorporate advanced techniques, allowing developers to focus on solving the problems effectively while ensuring efficiency and reliability. Efficient utilization of hardware resources is essential for improving performance when working with large datasets. One important strategy is to avoid CPU starvation by providing compressed data instead of raw data, as compressed data reduces memory usage and minimizes data transfer time, allowing GPU to process information more efficiently. Additionally, GPUs can be used for parallel computations as they offer significantly higher throughput compared to CPUs and are particularly suitable for tasks such as deep learning and large-scale matrix operations. On the CPU side, multi-threading can be used to execute multiple tasks simultaneously, which enhances performance for workloads that can be parallelized. To achieve optimal efficiency, it is important to balance the use of different hardware components. CPUs should handle general purpose processing, GPU should be used for computationally intensive parallel tasks, and memory should be efficiently managed to ensure fast data access. Reducing computing needs. Reducing computing needs is essential for improving efficiency and performance when working with large data sets. One of the first steps is to profile the code using appropriate tools to identify slow or inefficient sections, allowing developers to focus on optimizing bottlenecks. It is always better to use optimized and compiled libraries instead of writing manual loops in Python, as these libraries are faster and more efficient, especially for numerical computations. Data wrangling, also known as data munging, is the process of transforming and mapping data from its raw, unstructured form into a more structured and meaningful format that is suitable for analysis and further processing. Raw data collected from various sources is often incomplete, inconsistent, or not directly usable. So data wrangling helps in refining and organizing it. This process involves multiple steps such as cleaning, restructuring, and enriching the data to improve its quality and usability. The primary goal of data wrangling is to ensure that the data becomes accurate, consistent, and valuable, enabling effective analysis and supporting better decision making in downstream applications such as data analytics and machine learning. Data wrangling process involves 6 steps, namely discovery, organization, cleaning, data enrichment, validation, and publishing. Data wrangling involves several important stages that ensure raw data is transformed into a reliable and usable format. The first stage is discovery, where the data sources, structure, and key variables are understood and issues such as missing values or inconsistencies are identified. This is followed by organization, where the data is structured into a proper format such as tables or databases with correct labeling, indexing, and consistent formats. The cleaning stage focuses on removing errors, duplicates, and handling missing or inconsistent values, while also standardizing the data to improve its accuracy. Next, data enrichment enhances the dataset by adding new features or integrating external data sources, thereby increasing its value and usefulness. The validation stage ensures that the data is accurate, complete, and consistent, meeting the required quality standards before analysis. Finally, in the publishing stage, the data processed is prepared, shared in appropriate formats so that it can be used effectively for analysis, reporting, or visualization by stakeholders or systems. Data wrangling plays a vital role in real-world applications such as fraud detection and customer behavior analysis. In fraud detection, raw transaction data is collected from multiple sources like banks and payment systems, which often contain missing or inaccurate entries. Data wrangling helps in cleaning these records and standardizing formats such as dates, currency values, and transaction IDs, making the data consistent and reliable. This process data enables the identification of unusual patterns such as sudden large transactions or repeated suspicious activities, which may indicate fraudulent behavior. In customer behavior analysis, data is gathered from various sources, including purchase history, browsing activity, customer feedback, and demographic details. The data wrangling is used to merge this data from different platforms, remove duplicates, and resolve inconsistencies. A variety of tools are available for data wrangling, each designed to support tasks such as gathering, importing, structuring, and cleaning data before it is used in analytics and business intelligence applications. Spreadsheets and Excel Power Query are among the most basic and widely used tools, allowing users to manually clean and transform data with ease. OpenRefine is a more advanced automated data cleaning tool that can handle complex transformations, although it may require some programming language. Tabula is particularly useful for extracting data from different types of documents, especially tables and PDFs. Google Data Prep is a cloud-based service that helps in exploring, cleaning, and preparing data efficiently. Data Wrangler is another tool focused on transforming and cleaning data into a structured format. Additionally, Plotly is used with Python, supports data wrangling along with powerful visualization capabilities, especially making it useful for preparing data for charts and maps. The main benefits of data wrangling include data consistency, improved insights, and cost efficiency. Maintaining data consistency is essential for ensuring reliable analysis, as organizing and standardizing data helps to achieve uniform formats and reduces errors or mismatches across datasets. When data is clean and well structured, it significantly improves the quality of analysis by enabling more accurate statistical computations and meaningful interpretation of results. This leads to better insights as consistent data allows patterns and trends to be identified more effectively. Additionally, efficient data preparation contributes to cost efficiency by reducing the time and effort required for cleaning and processing data. This streamlined approach not only speeds up analysis but also enhances the efficiency of model building, ultimately resulting in long term savings in both computational resources and human effort. When working with datasets in pandas, data processing typically involves three key steps: cleaning, transforming, and merging. Cleaning focuses on improving data quality by handling missing values, removing duplicate records, and correcting inconsistencies to ensure data is accurate and reliable. Transforming involves modifying the data into a suitable format for analysis, which may include changing data types, applying functions, normalizing values, and performing feature engineering to create new useful variables. Finally, merging is the process of combining multiple datasets into a single unified dataset, allowing for more comprehensive analysis by integrating information from different sources. Together, these steps help to prepare the data for effective analysis and decision making. This example demonstrates how missing data can be handled effectively using pandas. Initially, the dataset is created with some missing values in the name, age, and city columns. The data frame is then processed into two different ways. First, drop any function is used to remove all the rows that contain any missing values, resulting in a clean dataset with only complete records. However, this approach may lead to loss of useful data. To address this, the fill NA function is used as an alternative where missing values are replaced with meaningful defaults. For example, missing names and cities are replaced with a value unknown, while missing age values are filled with the average age of the existing date. This approach preserves all the records while ensuring that the dataset remains complete and suitable for further analysis. This code demonstrates various data transformation techniques using pandas to make data more meaningful and suitable for analysis. Initially, a data frame is created with basic information such as name, age, and city. The transformation process begins by applying functions to columns, where a new column called age category is created using the apply function to classify individuals as young or old based on their age. Next, data type conversion is performed using the ASTag function to ensure that the age column is in integer format, which is important for consistency and accurate computations. The columns are then renamed using the rename function to improve clarity, for example, changing name to full name. Finally, a new column is created using the assign function, where age underscore square is calculated by squaring the age values, demonstrating feature engineering. These transformations enhance the structure, readability, and usefulness of dataset for further analysis. Thank you.